Hi, Assalamualaikum everyone. I am Farah Hamizah from University Science Islam Nation. Today, I will be presenting on my research work. The title of the research is Material Properties and Characterization of Carbon Nanotube Catalyzed by Mid-Scale for Electromagnetic Wave Absorber. My supervisor is Dr. Fazida Muhammad Idris and Dr. Syahidah Suhaimi. First, I will start with an introduction. Electromagnetic radiation is generated from natural environment such as solar energy and from human-made sources. With scientific and technological advancement, our everyday environment are filled with various human-made electromagnetic fields (EMF). These EMF are invisible and there are two main categories of EMF, which are the first one is extremely low frequency ELF and the second one is radio frequency RF waves. Where are this radiation comes from? So, ELF can be generated from electrical lines or transmission towers, while RF can be generated from mobile phones and smart devices. Consequently, the transmission of unwanted electromagnetic radiation to an electrical or electronic device can cause electromagnetic interference (EMI) pollution. These signals interfere with the device operation and can cause significant harm to human health, such as dizziness. For prolonged exposure to EMI may cause brain tumor and cancer. Therefore, we come up with a solution through this study. The objective of this research is to propose a solution to deal with EMI pollution, which is by producing an electromagnetic absorber, as well as having characteristics such as lightweight, low cost, and able to absorb in a wide range of frequency. An electromagnetic absorber can significantly reduce or eliminate EM radiation by the energy conversion or disruptive interference. From the figure of the mechanism, an incident EM wave through EM absorbing material undergoes three processes, which is the first one is reflection, absorption, and penetration. Let's move to the next slide, the methodology. In this research, I propose to use industrial waste, which is mid-scale, because it contains highly infrared. The sample preparation starts with washing mid-scale flakes and dry it. After that, we crush the mid-scale by using high-energy ball milling (HEBM). The step continues with the preparation of grooved carbon nanotube (CNT) by using chemical vapor deposition method, which is mid-scale as a catalyst, and also we use ethanol as a carbon source, argon gas as a carrier gas. The CNT mixed homogeneously with resin and then poured into a square mold shape and let dry for overnight at the room temperature. The result comes out as a flexible EM wave absorber. There are several ways to grow carbon nanotube, such as chemical vapor deposition (CVD) method, arc discharge, and laser ablation. Among them, the most common and recent method used is CVD because of low cost and continuous mass production. This is the schematic diagram of chemical vapor deposition CVD method that has been used in this study. The catalyst used is mid-scale that contain highly in ferrum, nickel, and cobalt. The temperature used is 700 degrees Celsius. The carbon sources is ethanol, and the carrier gas is argon gas. Next, the result and discussion. The data indicate results from XRD and Raman. X-ray diffraction measurement was taken on a Rigaku Miniflex 600 diffraction system to evaluate the crystal structure. As shown in Figure 1, the result exhibit the occurrence of CNT peaks at 26.2 and 42.8, corresponding to 002 and 100 diffractions of CNT. The broader and wider peaks were obtained for sample mine using high-energy ball milling, which indicates smaller particle size due to high energy impact to the mid-scale powder during milling process. Next, Raman shift spectroscopy was recorded using Raman Horiba with a 532 nanometer excitation wavelength to observe more detailed structural information on the carbon nanostructure. There are two main peaks in the Raman spectra, which are known as D-band and G-band. D-band, which originated from the structural defects, disordered carbon in carbon materials formed at around 1251 cm1, while G-band originated from graphite structure in plant vibration of sp2 carbon atom formed at around 1491 cm1. The integrated intensity ratio, ID over Ig, for the D-band and G-band are almost constant at around 1 for all the sample, which lead to a lower gravitization degree. In other words, it gives an advantages for the microwave absorption. Next, the result from field emission scanning electron microscope FISEM of acetized CNT on mid-scale mined for 4 and 8 hours. The figure shows the presence of entanglements due to a strong van der Waals forces. The carbon structure forms were mostly straight, spiral, and twisted. There are also net-like fibers which were formed by the aggregation of very fine fibers and particles like carbon. Basically, by having a carbon coil-like structure, it may result in having wide application, for example, as an absorbing material. Other than that, short fibers might improve the performance of EM wave absorption compared to microparticles. As per result discussed, we conclude that a lightweight and flexible EM wave absorber is designed by synthesized carbon nanotube from a mid-scale waste. The second conclusion is the presence of CNT is proved by the result of XRD and Raman spectroscopy, which indicate the success of lowering the cost of CNT filler. And the last conclusion, the microstructural behavior of CNT from mid-scale shows the potential to be one of the excellent EM absorber applied in broad-range frequency. This is the references that we use to refer the article. That brings me to the end of my presentation. Thank you for listening.